Assalamualaikum, my name is Inaz, Batrisyia, and my group members are Mariah, Qistina, and Umi Syahira. We are from CS 1124B. For today's presentation, we will be presenting about problem solving with inverse matrix in investment strategy. So now, we will get into the introduction of this case study. In this case study, we examine a practical scenario where a company is seeking to optimize its investment strategy by analyzing various investment options and the expected returns. The company's goal is to allocate a fixed budget across three distinct investment options to maximize its overall returns. Each investment option is represented by a set of linear equations which encapsulate the relationship between the investment amounts and the expected returns. This scenario provides an ideal opportunity to demonstrate the application of inverse matrices, a fundamental concept in linear algebra in solving real-world problems. So now, we will get into detail on the case study, which is an investor under Blockbook Company aims to determine the optimal investment strategy for the company. In order to achieve the goal, the investor planned to put some company's capital into various potential investment options. After reviewing the expected return of the investment, the investor decided to invest in three different investment options of stocks, bonds, and mutual funds. The risk-to-reward ratio plan of each option is firstly Plan A, which is 2,000 return, 2%, 3%, and 1% from stocks, bonds, and mutual funds respectively. Second, Plan B, I am 2,500 return, which is 1%, 2%, and 4% from stocks, bonds, and mutual funds respectively. Or lastly, Plan C, 2,500 return, which is 3%, 1%, and 2% from stocks, bonds, and mutual funds respectively. Now next, we go into the purpose of this case study, which is the primary purpose of this case study is to illustrate how inverse matrices can be utilized to solve a system of linear equations in the context of optimizing investment strategies. By representing the investment options and their expected returns through a matrix equations, we can employ the inverse of the coefficient matrix to determine the optimal amounts to be invested in each option. This approach not only simplifies the calculation process, but also highlights the practical importance of linear algebra in financial decision-making and resource allocation.
Problem statement of this case is how much fund needs to be put into each investment option in order to receive the expected return. To solve this problem, we know that each option can be represented by a set of linear equations which encapsulate the relationship between the investment amount and the expected return. The first equation that can be generated is 2x plus 3y plus z is equals to 20. The second equation is x plus 2y plus 4z is equals to 25. The third equation is 3x plus y plus 2z is equals to 25. This equation is a result from dividing all the numbers with 100. Variable x, y, and z is the amount to be invested in each investment option, where x is for stocks, y for bonds, and z is for mutual funds. First step is to convert the linear equation into matrix A and B. The first column in matrix A represents as x, the second column represents as y, and the third column represents as z, while matrix B is the expected return of each linear equation. The second step, we need to let AX equals to B, where A is the coefficient matrix, X is the variable matrix, and B is the constant matrix. Third step is to find A inverse. We acknowledge that we need to transform matrix A into identity matrix in order to get A inverse. First, we need to combine two matrices, matrix A and identity matrix, into an augmented matrix. We can reduce the matrix A into identity matrix using the elementary row operation method. We can see that the first non-zero entry for the first row is 2, and to make it 1 as the leading one for the first row, we need to interchange the first row with the second row. The leading below leading 1 is 2 in the second row and 3 in the third row. To make it 0, we need to multiply the first row with -2 and add it to the second row. For the third row, we need to multiply the first row with -3 and add it to the third row. Proceed to the second row. To make the non-zero entry 1, we need to multiply the second row with -1. As we can see, the entry below the leading one is -5. To make it 0, we need to multiply the second row with -5 and add it to the third row. Proceed to the third row. To make the first non-zero entry 1, we need to multiply the third row with 1/25. Now the matrix is in the row echelon form. We still need to transform the row echelon form into the reduced row echelon form. To make it happen, we need to observe that other entries than the leading one are all 0. The entries above the leading one in the second row is 2. To reduce it, we can multiply the second row with -2 and add it to the first row. The same step we do to the entries above the leading one in the third row, but now we multiply -7 into the third row and add it to the second row. Now we can see that the entries above the leading one on the third row, which on the first row is not 0. So we can reduce it by multiplying the third row with 10 and add it to the first row. Matrix A has reduced to identity matrix, so the matrix that we get on the right side is the inverse of matrix A. First step is to find X. Referring to the theorem, we know that inverse of matrix A multiplied by matrix A is equals to identity matrix. To cancel off matrix A from the left-hand side, we need to multiply with inverse of matrix A on the both sides. On the left-hand side, we know that identity matrix multiplied by variable matrix is equal to variable matrix. While on the right-hand side, we can see that the number of column in the first matrix is equals to the number of row in the second matrix. From this, we know that size of matrix X is 3 by 1. So, we can do a matrix multiplication. In order to find the value of the first column in matrix X, we need to multiply all the elements in the first row in inverse of matrix E with the corresponding element in the first column of matrix B and summing up all these products. The same step we use to find the second row and the third row of matrix X. Based on steps earlier, we know that X is denoted to the matrix of X, Y, and Z. Now, we can find X, Y, and Z, where X is 5, Y is 2, and Z is 4.
As for the results, the amount that is required to be invested in the three investment options are for X, which is stocks, is equals to 5, Y, which is bonds, is equals to 2, while Z is mutual funds, which is equals to 4. Therefore, by using the inverse matrix method, we can solve our problem to identify the amount of funds that needs to be invested into each of the three investment company, which are stocks, bonds, and mutual funds, in order to receive the expected amount of expected returns. This can be done by using the risk to reward ratio plan, which is for plan A, which the return is 2,000 ringgit Malaysia. The ratio is 2% of stocks, 3% of bonds, and 1% of mutual funds. For plan B, which the return is 2,500 ringgit Malaysia, the ratio is 1% of stocks, 2% of bonds, and 4% of mutual funds. While for plan C, which the return is 2,500 ringgit Malaysia, the ratio is 3% of stocks, 1% of bonds, and 2% of mutual funds. Thus, the calculation from the previous methodology has shown that it is proven that we managed to use this approach to find the amount of funds. In conclusion, this case study successfully demonstrates the application of inverse matrices in solving a real-world problem related to investment optimization. By leveraging the power of linear algebra, we can effectively determine the optimal allocation of resources to maximize returns. This approach not only simplifies complex calculations, but also underscores the importance of mathematical concepts in making informed financial decisions. The ability to solve systems of linear equations using inverse matrices proves to be a valuable tool in various fields, including finance, economics, and operations research.